we discuss engineering mathematics. In engineering mathematics, we have 7 chapters. Let me tell you 7 chapters. Chapter 1 is linear algebra. Chapter 2, differential equations. Chapter 3, calculus. Again, in calculus, we have 3 different modules: differential calculus, integral calculus, vector calculus. The 4th chapter is probability and statistics. Next one, numerical methods. Next one, complex variables. And at the end, we have a transform theory, which includes Laplace transforms, Fourier transforms, and jet transforms. Right? Even let us discuss the individual weightage of all these points. When you look at linear algebra, that is chapter 1, we have weightage of 2 marks. Calculus, weightage 4 marks. That is from differential calculus, integral calculus, vector calculus, it will be approximately 4 marks. Numerical methods, 2 marks. Probability statistics, 2 marks. Transform theory, 1 mark. Complex variables, 2 marks. Differential equations, 2 marks. So approximately there will be exactly 15 marks from engineering mathematics. Right? Now in this session we discuss linear algebra, that is chapter 1. So today in this session particularly we discuss basic definitions followed by various examples followed by conclusions, notes, remarks, etc. Right? Now let us start with a definition of matrix. What is a matrix? It is defined as arranging elements in the form of rows and columns. It is defined as arranging elements in the form of rows and columns is called a matrix. Let us start with an example. Suppose I have 4 elements, 1, 2, 3, 4. Now I can arrange all these 4 elements in the form of 2 rows, 2 columns, 4 rows, 1 column, or 1 row, 4 columns. Let us follow this size. If I maintain these 4 elements in the form of 2 rows and 2 columns, the structure will be like this. So matrix structure will be like this: 1, 2, 3, 4. Or I can do like this. If I follow this sequence, 4, 1, 4 rows, 1 column. So like this: 1, 2, 3, 4. Or I can do like this: A equal to 1, 2, 3, 4. So 1 row and 4 columns. So this is 1 by 4 matrix, this is 4 by 1 matrix, and this is a 2 by 2 matrix. So what is a matrix? Arranging elements in the form of rows and columns is called a matrix. Even if I follow different sequence in these elements, among these elements, so finally there will be exactly 3 different sizes: 2 by 2 size, 1 by 4 size, and 4 by 1 size. Write the definition. Matrix. Arranging elements in the form of rows and columns. Arranging elements in the form of rows and columns is called a matrix. Arranging elements in the form of rows and columns is called a matrix. Note down these 3 examples. Right. Next definition: order or size or dimension. Order or size or dimension. Suppose I have a matrix A. Since it is a matrix, it has some rows and some columns. Generally number of rows is denoted by and number of columns is denoted by n, and its size is denoted by m cross n. So where m is nothing but number of rows and this n represents the number of columns. So here I mentioned 3 different words: order, size, dimension. Everything is same. How to define this? The number of rows and columns of a matrix is called size of a matrix. So it is denoted by m cross n, where m represents number of rows and n represents number of columns. At first we write number of rows, at last we write number of columns. Write the definition. The number of rows and columns of a matrix. The number of rows and columns of a matrix is called size of a matrix. The number of rows and columns of a matrix is called size of a matrix. First off, it is denoted by m cross n. It is denoted by m cross n, where m is number of rows and n is number of columns, where m is number of rows and n is number of columns. So in the future, sometimes I may use the notation dimension, sometimes I may use the word size, sometimes I may use the word order. Everything is same, right? Now we discuss various types of matrices. Next definition is square matrix. Now, before discussing square matrix, let us observe the word square. When you observe square object, its important property is number of rows and number of columns are same. That is for matrix. When you look at square object, this row-wise representation is called length and column-wise representation is called breadth. Got it? So length corresponds to number of rows, breadth corresponds to number of columns. So a matrix in which number of rows is same as number of columns is called a square matrix. Right? Let me give a few examples. Suppose if I take A equal to, for example, 1, 2, 3, 4. Now it has 2 rows and 2 columns. Now you can see here the number of rows is 2 and the number of columns is 2. So this is an example of a square matrix. Suppose if I take 3 by 3 matrix, suppose 1, 2, 8, 2, 9, 6, minus 1, 0, 4. Now the size of this matrix is 3 by 3. Now in this case, the number of rows and number of columns are same. So these two are examples of square matrices. Note this point. A matrix in which number of rows is same as number of columns. A matrix in which number of rows is same as number of columns is called a square matrix. Note down these two examples. First example, example 2. Next definition, rectangular matrix. Now, in a rectangle, what is the property? In a rectangle, this corresponds to length. Basically, length represents number of rows and this is breadth, B. Breadth corresponds to number of columns. So in a rectangle, length value should not be equal to breadth value. So if length does not match with breadth, then it is called rectangular object. So in the similar fashion, a matrix in which number of rows is not same as number of columns is called a rectangular matrix. Or in simple words, a matrix which is not square is called a rectangular matrix. Two different objects. One is square and there is rectangle. If number of rows is matching with number of columns, it is a square. If both are different quantities, then it is called a rectangular matrix. Let's take an example. Suppose if I take A equal to 2, 1, 3, 4 minus 9, 6. Now the size of this matrix is 2 by 3 because it has 2 rows and 3 columns. First row, second row, first column, second column, third column. So the size of this matrix is 2 by 3. So here m value and this is n value. So here number of rows is not matching with number of columns. So this is an example of a rectangular matrix. Note this. A matrix which is not square is called a rectangular matrix. A matrix which is not square is called a rectangular matrix. You can have any example. Just you can maintain this 2 by 3 example. Right. Next concept. Equality of matrices. Equality of matrices. Suppose we have two matrices, say A comma B. First matrix is A, second matrix representation is B. We say that these two are equal if they satisfy two properties. Property 1 is the size of A must be same as size of B. Second one is corresponding elements in A comma B should be equal. So whenever two matrices A comma B satisfy these two properties, then we say that A and B are equal. Symbolically we write it as A equal to B. So what is the first point? Regarding sizes, both must have same size. If the size of A is 2 by 2, size of B must be 2 by 2. If the size of A is 4 by 7, then size of B must be 4 by 7. So sizes point of view, they must have same size. And second point is corresponding elements are same. That means position wise elements are same. So if you ask me this element is in which position, that means in which row and which column this element is available. So I can use one particular notation. Suppose if I follow this notation, if I say this, for example, A2, 3. So what does it mean? This is the third element in the second row. Third element in the second row. Or this is this is third element in the second row. Or this is second element in the third column. Like this. So it represents row number and this represents column number. So this can be viewed in two different ways. Third element in the second row or second element in third row, third column. Now therefore whenever two matrices follows that these two things, then we can say that A equal to B. Let us take an example. Suppose A equal to 2, 1, 8, 4. The size of this matrix is 2 by 2. Suppose B 2, 1, 8, 4. Its size is 2 by 2. Now in this case, the sizes are equal for both the matrices. The first matrix size is 2 by 2, second matrix size is 2 by 2. So point 1 is very clear, sizes. Now corresponding position wise element, first element in the first row, first element in the first row, second element in the first row, 1 is matching with 1, 8 is matching with 8, 4 is matching with 4. Therefore in this case I can maintain like this. So here I can say that A11 equal to B11 and A12 equal to B12, A21 equal to B21 and A22 equal to B22. So this is the meaning of corresponding elements are equal. Therefore in this case A is equal to B. Suppose if I consider another matrix, now I am going to give an example in the negative direction. Suppose C equal to this. For example 2, 1, 3, 8, 4, 9. Now its size is 2 by 3. Now in this case, the size of A is not matching with size of C. That means the first property is getting failed. So when at least one property fails, the overall statement is false. Generally, in the area of mathematics, if you want to say that a statement is valid, it must be true in all possible cases. But if you want to say that the result is false, just give an example. Just give an example, and such examples are called counterexamples. Right? We always come across with counterexamples. If you want to say that a statement is false, just prove that by taking an example. But don't take examples to prove that some statement is true. But if you want to say that some statement is false, give an example. Such examples are called counterexamples. That means we are giving some counter in the negative direction. So whatever you say, the statement is wrong, by which I'm giving justification by an example. Such examples are called counterexamples. So therefore, in this case, the size of C is not matching with size of A, so A is not matching with C. Or suppose if I take D like this, for example, 2, 1, 8, 9. Here the size of D is 2 by 2. Now in this case, the size of A is 2 by 2 and size of B is 2 by 2. So first element 2 is matching with 2. 1 is matching with 1, 8 is matching with 8, but 4 is not matching with 9. That means in this case A22 is not matching with D22. Therefore in this case A is not matching with D. I think all these points are very clear. Note down these points. Two matrices A comma B. Two matrices A comma B are said to be equal. Two matrices A comma B are said to be equal if they satisfy the following. If they satisfy the following. First one, the sizes of A comma B are same. The sizes of A comma B are same. Second point, the corresponding elements in A comma B are same. The corresponding elements in A comma B are same. Now write these two examples, one in the positive direction, second example in the negative direction. Next concept, transpose. Suppose we have a matrix A with size m cross n. Here m can be equal to n or m need not be equal to n. Now let us define the transpose of this matrix. The transpose of this matrix is denoted by A power t. Even this is also a matrix which is obtained from capital A by interchanging corresponding rows and columns. Just suppose if the size of A is 2 by 3, then its transpose size will be 3 by 2. Let me tell you how the size will be reversed. Suppose A contains 2 rows and 3 columns. So how the size will be reversed in case of its transpose? So make the first row as first column, make the second row as second column. That means indirectly rows are becoming columns and columns are becoming rows. In that case size will be reversed. So therefore the matrix obtained from a matrix A by interchanging corresponding rows and columns is called transpose of a matrix A. Symbolically it is denoted by A power t. So therefore in this case what could be the size of A transpose? This will be n cross m. Say for example, if I take element matrix like this, A equal to 2, 1, minus 3, 8, 9, 6. So the size of this matrix is 2 by 3. Now A transpose A power t. So make the first row as first column. So 2, 1, minus 3. Make the second row as second column. Now it becomes 8, 9, 6. Now let us see the size of this matrix is 3 by 2. Earlier 2, 1, 2, 8 is first column. Now it became first row. 1, 9 is second column. Now it becomes second row. Now minus 3, 6 third column. Now it became third row. Therefore rows became columns and columns became rows. Therefore this is the transpose of this matrix. So the conclusion from this definition is, if the size of A is m cross n, then the size of A transpose is n cross m. Write the definition. Let A be any matrix. Let A be any matrix. First off, the matrix obtained from A, by interchanging corresponding rows and columns. The matrix obtained from A by interchanging corresponding rows and columns is called transpose of A. It is denoted by A power T. Write this example. Note, if the size of capital A is m cross n, then the size of A power T is n cross m. I am repeating once again. If the size of A is m cross n, then the size of A power T is n cross m. Next one, properties of transpose. We have 4 important properties. Suppose A comma B are 2 matrices. Now, when I add 2 matrices, I will get another matrix of same size. So, regarding addition, both must have same size. Now, I am adding matrix B with A. So, the size of A and B must be same. The same case even valid for minus also. So, A and B are 2 matrices of same size. Both can be square or rectangular, but same size, at least for first property. So, then I can add A and B, or I can subtract one matrix from first matrix. I will get another matrix. So, the transpose of this is A transpose. If it is plus, we get plus. If it is minus, we get minus. So, A plus or minus B whole transpose is A transpose plus or minus B transpose. Second property, A transpose whole transpose. So, when you transpose a matrix twice, you will get the same matrix. Property 3, K into A whole transpose. Here K is some constant, A is some matrix. This constant can be taken before this matrix A transpose. So, K A transpose is K into A transpose for any constant K. Fourth property, this is regarding multiplication, A into B whole transpose. See, here I am multiplying A with matrix B. We know the basic criteria to multiply 2 matrices. What is that criteria? If I want to multiply B with A in this direction, see, direction multiplication order is important because A into B is may be different from B into A. Sometimes they may be same, sometimes they may be different. So, if you want to multiply A with B in the direction A into B, then the number of columns in A must be same as number of rows in the first matrix B. Like this. Suppose if the size of A is 2 by 3, then the size of B must be 3 cross, for example, n. So, here the number of columns in the first matrix must be matching with number of rows in the second matrix. So, if the sizes of A and B are like this, then they are flexible for multiplication. Then the size of AB becomes 2 cross n. It's a fundamental basic. Therefore, assume that A and B are flexible for multiplication. Therefore, in this case, when you calculate AB whole transpose, we get result in the negative reverse direction, B transpose into A transpose. If you apply this for 3 different matrices, ABC whole transpose becomes C transpose into B transpose into A transpose. Note all these points. Now, based on these properties, let us conclude one point. That's a relation basically which connects a matrix, square matrix A, in terms of its symmetric part and in terms of its skew symmetric part, right? Based on these 4 properties, very, very important point. Suppose I have a matrix A, size n cross n, square matrix. Then this A can be written as half into A plus A transpose plus half into A minus A transpose. This is very clear. So a square matrix A can be written like this: half A plus half A, full A, half into A transpose minus half into A transpose gets cancelled. Now let us see what is the benefit for this. This is one matrix B. I call it as this is another matrix C. So here what is matrix B? Half into A plus A transpose. C is second matrix, half into A minus A transpose. Now what I am going to prove is, I prove that this B is symmetric matrix and C is skew symmetric matrix. So in this case, when I go for its properties, I can easily get its transpose. So therefore in this case, when I go for B transpose, this I can get it as half into A plus A transpose whole transpose. This is constant into matrix whole transpose. Apply this property number 3. So constant can be taken before transpose, half into A plus A transpose whole transpose. This is half into A plus B whole transpose. Apply property 1. This becomes A transpose plus A transpose whole transpose. Therefore, in this case, this is half into A transpose plus A. Now, again, we got the same matrix B. In the similar way, when you calculate C transpose, you will get exactly minus C. Now, here B transpose is B. That means B is a symmetric matrix. C transpose is minus C. C is a skew symmetric matrix. Therefore, this B is a symmetric matrix and C is a skew symmetric matrix. I discuss this point shortly. What will be the elements of symmetric matrix, what will be the diagonal elements of skew symmetric matrix, how they look like, what is the connection between elements in some pattern. Let me explain after some time. But for the time being, you try to understand when B transpose is equal to B, then it is called symmetric matrix. When the transpose of a square matrix is negative of original matrix, then it is called a skew symmetric matrix. And even in this case, this B is called symmetric part of A and C is called skew symmetric part of A. So what's my conclusion? Every square matrix A can be expressed as the sum of symmetric and skew symmetric matrices. Every square matrix A can be expressed as the sum of symmetric and skew symmetric matrices. Note this point. Every square matrix capital A can be expressed as the sum of symmetric and skew symmetric matrices. Can be expressed as the sum of symmetric and skew symmetric matrices. To justify this statement, note all these points. Even this is very simple to verify. Just for normal calculations, you will get C transpose equal to minus C. Next definition, symmetric matrix. Suppose I have a square matrix A of size n cross n. We say that this is symmetric matrix if A is same as A transpose. So whenever A is same as its transpose, then this is called a symmetric matrix. That means matrix must be equal to its transpose. Let us take an example. Suppose A equal to 2, 1, 4, 9, for example. Now in this case, when you look at the elements, this element 1 is, this is A1, 2. Second element in the first row, this is second element in the first row, or first element in the second column. Now this element is A21. So in this case, A12 is different from A21. Therefore, the matrix cannot be symmetric. Suppose if I take this A equal to suppose 2 1, then this must be 1. Suppose 1 8. Now in this case A transpose also will be same as 2 1 1 8. Now in this case these are my diagonal elements 2 8. Why they will be called as diagonal elements? Because when you consider a square object, you will be having two diagonals. This is one diagonal, leftmost diagonal. Another diagonal is this rightmost diagonal. Always focus on this leftmost diagonal. So what is the speciality of elements in the leftmost diagonal? Indexes will be same. Suppose if you consider a 3 by 3 matrix A. So what will be my diagonal elements? A11, A22 and A33. That means I value, J value will be same. So therefore if I write AII, it refers to diagonal element. Therefore what I mean to say is, when you are constructing an example of symmetric matrix, you need not worry about diagonal elements, leftmost diagonal elements. Basically we call them as principal diagonal elements. So whenever I discuss diagonal elements, you always give priority for leftmost diagonal. You don't bother about non-diagonal elements. So in case of symmetric matrix, my diagonal elements are leftmost diagonal elements. They are simply dummy elements. If you want to construct a 2 by 2 symmetric matrix, you randomly assign your own values. But regarding non-diagonal, there must be some relation connecting that. That equation is, in this case, A equal to A transpose. So this is a matrix-wise comparison. When you go to element-wise comparison, this is A12, this is A21. So therefore, A12 must be equal to A21. Suppose when you consider 3 by 3 matrix, 3 by 3 skew symmetric matrix, randomly assign some elements, for example 2 1 9, diagonal elements. If it is -8, this must be -8. This is 6, this is 6. Suppose this is 7, this is 7. So in this case what happened is, this -8 is A12, this is A21. So A12 equal to A21. This is A13, this is A31. So A13 equal to A31. This is A23 and this is A32. So A23 equal to A32. Therefore, indirectly what I mean to say is, Aij must be equal to Aji. Aij must be equal to Aji for all I comma j. This is the definition of symmetric matrix by comparing element wise. This is the definition of symmetric matrix by matrix wise comparison. Right? So, write the definition. A square matrix A is said to be symmetric. A square matrix A is said to be symmetric if A equal to A power t. If A equal to A power t, or small aij equal to Aji, Aij equal to Aji for all I comma j. This is an examples, first example, and this one is second example. Both are symmetric matrices. Note down example 1, example 2. This is an example of a non-symmetric matrix. Because of this difference, 1 is not matching with 4. Here A should not be matching with A transpose. So this is a non-symmetric matrix. As definition, skew symmetric matrix. Suppose we have a square matrix A. We say that this is skew symmetric if A is matching with minus A transpose. Minus A transpose means multiply every element of A transpose with -1. So equivalently, this is nothing but Aij equal to minus Aji for all I comma j. This is matrix wise comparison. This is element wise comparison. Just minus symbol will come extra. In case of symmetric, minus will not be there. In case of skew symmetric, minus symbol will come. So whenever a square matrix A satisfies this or this, then this is called a skew symmetric matrix. Now before constructing an example of skew symmetry, let us discuss what will be the structure of elements of diagonal in case of skew symmetric matrix. Here Aij equal to minus Aj for all I comma j. Since Aij is equal to minus Aj for all I comma j, this is true for all I comma j. So if j equal to I, that means my focus is on diagonal elements. Then this equation becomes Ai equal to minus Ai. J equal to I means they refer to diagonal elements leftmost. So Ai equal to minus Ai. So to Ai equal to 0. This implies Ai equal to 0. Therefore, the conclusion from this point is, if something is a skew symmetric matrix, all elements along diagonal must be equal to 0. So this is one of the point which we can get directly from definition, right? Now it makes us very simple to construction of examples of skew symmetric matrices. Suppose if I start with a very lower dimension, 1 by 1. See how many elements will be there in a 1 by 1 matrix? Only one element, that is A11. As we know that in any skew symmetric matrix, all elements along diagonal are 0. Therefore, if you ask me to construct 1 by 1 skew symmetric matrix, this will be 0 only. So this is an example of 1 by 1 skew symmetric matrix. When you consider 2, I go for larger dimension. Now let us fix diagonal elements to 0. So suppose if I fix minus 2, this could be 2. Suppose if I go for 3 by 3 skew symmetric matrix, let us fix diagonal elements to 0 at first. Now this is minus 1, plus 1. This is 8, this is minus 8, this is 0.3 and this is minus 0.3. Therefore, all these are examples of skew symmetric matrices. Write the definition first. A square matrix A is said to be skew symmetric. A square matrix A is said to be skew symmetric if A equal to minus A transpose, or A is A equal to minus Aj for all I comma j, or A is A equal to minus Aj for all I comma j. Let's continue these lines till this point. Note, if A is a skew symmetric matrix, then all elements along diagonal are 0. Then all elements along diagonal are 0. Next examples. Note down example 1, 2, 3. 1 by 1, 2 by 2, 3 by 3. Even the interesting point in example 1 is, this can be viewed as a symmetric matrix also. So a 1 by 1 null matrix means if all elements are 0, it is called null matrix. So a 1 by 1 null matrix is symmetric as well as skew symmetric. Now let us discuss the converse of this statement. Just now we proved that if something is skew symmetric, all elements along diagonal are 0. What is its converse? Converse means the reverse of a statement. See, I will give you one simple example. If a student studies well, then he or she gets good marks. General statement. If a student studies well, then he or she gets good marks. What is this converse? If a student has got good marks, does it mean that faculty has taught, if a student has got good marks, does it mean the student has studied well? May or may not be true. Let me give you one sample example just for fun. If a student, assume that the student has got good marks by doing some cheats and like this. So in that case, the student has got good marks, but he or she did not study well. So that is one example. You may give me 99 examples where the students have got good marks by studying very well. But it doesn't mean that by discussing one particular example in case of a single student, so then I can say that the converse is not true. So the converse in this particular context is, if all diagonal elements of a square matrix are 0, it may or may not be skew symmetric. The best counter example is this. So I am giving this example, A equal to 0, 2, 4, 0. Here all elements along diagonal are 0, but still this is not skew symmetric, right? Note this point also. Now the converse of above may or may not be true. The converse of above may or may not be true. That is, if all diagonal elements of a square matrix, that is, if all diagonal elements of a square matrix are 0, then matrix need not be skew symmetric. Then matrix need not be skew symmetric. Counter example, A equal to this, 0, 2, 4, 0. Now we discuss another point. Third point is, if at least one diagonal element of a square matrix is not equal to 0, then what do you say? I am repeating. If at least one diagonal element of a square matrix is non-zero, then the conclusion is it is not skew symmetric, right? Note this point. If at least one diagonal element of a square matrix is not equal to 0, if at least one diagonal element of a square matrix is not equal to 0, then matrix is not skew symmetric. Then matrix is not skew symmetric. I recall the last 3 points what we discussed. See, from the definition of skew symmetric, it is very clear that all elements along diagonal, leftmost diagonal, are 0. So, what is the first point? If A is a skew symmetric, then all elements along the diagonal are 0. Second point, its converse. If all diagonal elements of a square matrix are 0, then matrix need not be skew symmetric. Even we have given one counter example. The third point is, if at least one diagonal element of a square matrix is non-zero, then the matrix is not skew symmetric, right? See, in the examination, in gate point of view, they may give you questions like this: which of the following is skew symmetric? Suppose if they increase the dimensions in different options, then just observe diagonal elements. Suppose unfortunately in every option, if all diagonal elements are 0, then you consider Aij. If at least one Aij is not matching with Aji, then it is not skew symmetric. So in that case, you can eliminate different options. So elimination method is one of the best way to get the answers very easily. So therefore, if the all concepts are very, very clear, even if you are unable to get the answer directly, if you are able to eliminate 3 options indirectly, then also you can get the answer. So make sure that all definitions are very, very important, not only in this subject. If all definitions are very clear in all areas, then clearing any competitive examination or understanding things is very simple. So try to understand all definitions followed by different examples, followed by important notes, etc. So it gives 50% confidence, it increases 50% confidence in your subject, right? Now this is the end of this particular session. Even in the next session also we discuss few basic definitions, concepts, examples. Thank you so much.